Alright, welcome my true Gemini. Today we are going to be looking deeper into Alkenes, more advanced preparations and reactions of Alkenes that you would want to know. Okay, so now we are going to be talking about preparations. I will give about like three or two advanced preparation. After that, we're going to look into more reactions that we advanced than the former video. Okay, so now first of all, in the other video, I gave basic um, preparations. Now I'm going to give you a more advanced preparation. And what is the first advanced preparation we're going to be looking into is the dehydrohalogenation of alkyl halides. Okay, we're going to be looking into the hydrohalogenation of alkyl halides. Okay, I believe we already know what halogenation means. The hydro, we know, we already know this term since we watched the former video. Okay, so now let's just dive into this. And first of all, before we do anything, we have to what? Write out the general formula in using to like prepare these alkenes with this particular method. Okay, so now first of all, the hydrogenation of alkyl halides. First of all, it has to do with what? Alkyl halides. So now let's write alkyl halides. This represents alkyl, these are halogens. So putting them together are now what? Alkyl halide. So now how do we now get alkenes from alkyl halides? We react with what? A caustic alkaline. It can be what? Sodium hydroxide or potassium hydroxide. When we react these two together in the presence of what? An alcohol. In the presence of an alcohol, what is going to happen? Now, the reaction is very simple. It's a displacement reaction that is going to happen. Now, if these two react, what are they going to form? They are going to form an alkene with what? Another compound is going to form here. We are going to have something like this. Potassium what? Halide. Okay, we are going to have something like this, and finally we are going to have water. This is how the general formula looks like. It's as simple as that. First of all, if you want to get this into your head, if you remember the name, the hydrogenation of alkyl halides, we now know first of all that it has to do with alkyl halides. Now, how come alkyl halide is going to give us alkene? That is when we come about what? The caustic alkaline. If you remember the caustic alkaline, the rest is just easy, and the catalyst involved. So when these two react to each other, what will happen? Double displacement reaction will take place, and they will like swap each other and all that. Then you've gotten your full equation. Okay, so now from this, now what do we do with this information? We have to do what? We have to impute an example to check if actually this thing is going to give us an alkene. Okay, see, at looking at that, first of all, the most important thing is that we have to choose an alkyl halide. After choosing an alkyl halide, we use our distance, and that's all. Okay, so on that note, what do? We pick an alkyl halide. So we can use what? Ethyl bromide. Ethyl bromide is going to be written as this: C2H5 bromide. We react with what? Potassium hydroxide. Now, from the look of things, what is this thing going to give to us? It's very simple. Now, we have our catalyst to be what? An alcohol. So now, exactly what happened here? A double displacement will happen. Now, first of all, we are going to get what? We are going to get an alkene. And which, from the look of things now, if you look at this, which alkene are we going to get? The nearest alkene we are going to get is definitely going to be ethane. Okay, C2H4. That's what we're going to get. Now, what will happen? This guy will come here and the other guy will go there. Okay, so what will happen now? We are going to have this potassium bromide. After getting our potassium bromide, what next? Water will be displaced. So now, from the look of things, we now know that any corresponding alkyl halide we are going to use is going to give us a corresponding alkene. You get? So it's as easy as this. But now, there's something I want you to know, a very very important point. Okay, first of all, we know this is what? Ethyl bromide. I just want us to know the names of what we're using. A caustic alkaline, potassium hydroxide to be precise. Then our catalyst. Then this guy is what? Our alkene, the corresponding alkene that we got here. Okay. So now, there is a very important point I want you to note about this. Now, the alcohol used in this reaction, in when we are studying alcohols, we have primary, we have secondary, and we have tertiary alcohols. So now, there is a degree of dehydrohalogenation of the alcohol. The tertiary alcohol has the highest what? Dehydrohalogenation power. You understand? So after the tertiary alcohol, what we follow is the secondary what? Alcohol, before we now get the primary alcohol. It's as simple as that. Like what in plain man understanding, in layman understanding, I just mean that the tertiary alcohol has, like, if it takes the tertiary alcohol 2 minutes to like undergo this reaction, secondary alcohol will take him like, let me say, 30 minutes, and primary it will take him something like 1 hour. You get the whole stuff, right? Okay, now so let's look into a way more advanced preparation also aside from this. Alright guys, now so the second what preparation we're going to be looking at in this video is what? We're going to be looking at the hydrogenation of vicinal dihalide. Okay, first of all, if you are looking into something like this, it's very very easy. You don't look at things you don't know. You focus on the ones you know. We already know what hydrogenation is, but dehydrogenation is simple, right? If hydrogenation means the adding of a hydrogen molecule, we know, then automatically we know the meaning of dehydrogenation. Okay, so now we know what dihalide means. Dihalides are compound which possess two what they call it, two substituents, which are halogens. Okay, so since we've gotten the key keywords we have to do, what do we do now? Now, how are we going to use dihalides, a dihalide compound, to get an alkene? First of all, we will need a dihalide compound to even get it at first. So now, let's write our general formula. Okay, now if we have a dihalide compound, for example, what do we use to represent halogens? We represent halogens as X normally. Okay, so now this is our dihalide compound. It possesses what? Two halogens. So now, if this guy reacts with what? If he reacts with a metal, example of metal that we can use is what? Zinc. If it reacts with zinc, what is this guy going to give to us? Now, something will happen. This single bond here will become what? Double bond. And when it becomes double bond, what will happen? These two halogens are no longer going to be here, because it's a reaction. As it reacts, this guy will form double bond, and these halogens will come, and it's like a displacement reaction. Okay, it's more like a displacement reaction. Now, what is going to happen? As I said, a double bond will be formed here, so we are not going to have what? And automatically we've gotten our alkene. What next? We are going to, because the react what we're interested now is this, but the reaction is not going to end like this. It's going to what? Form a zinc halide. I remember that always what they call it, the atomic. Halogens are always diatomic, they react diatomically. So this is how it's going to be. From the look of things, we can see that the reaction is actually balanced. Obviously, it's actually balanced. The two halogens are there. Your zinc that is here is also here. So the reaction is balanced. Now, what else do? We have to test it with an example. Now, key point you have to note about this preparation of alkene is that when a dihalide compound reacts with a metal, it will give us a corresponding what? Alkene. Okay? It will give us a corresponding alkene and form a compound with the metal. Alright? So now, we are going to take an example to check if actually this thing we are doing here is actually correct. Now, let's use a compound like this. Which halogen do we use? Let's use chlorine. Let's use chlorine. Then now we just have to balance our hydrogen. That's all. Okay. All right. So what do we have here? We have what? Propane. First of all, is propane. Single bond is propane. We have two chlorine. So we can just count. First of all, we have to count from the one closest to the substituent. So we have it to be what? 1, 2, 3. So we're going to have something like this. 1, 2 dichloropropane. Now this is the compound we are going to get. 1, 2 dichloropropane. Now if we react 1, 2 dichloropropane with what? A metal, what is going to happen? A double bond is going to be formed, because when this guy, when we remove the double the two halogens here, it will not be vacant and it's not going to be replaced by what? A hydrogen molecule, because there is no hydrogen. Obviously there is no hydrogen molecule here, so it will now close up and turn to what? Double bond. Okay, now what are we going to get? Now there is a very important and essential point you have to note about this. The position whereby the two halogens were before, that's where the double bond will be. The carbon holding the two halogens will be the one possessing the double bond. Okay, so now first of all we have to write our what? Prop. Now we identify where the what? Halogens are, and we know it from the last two carbon from this side. So we can just put it double bond. It's complete. We've gotten our what? Propane. Now what else do we now do? The reaction does not end like this after getting our corresponding what? Alkene. It will be continued to give us what? Zinc what? Chloride. Okay, now what do we now do? We have to just balance our reaction. Okay, we have to balance our reaction like this. Okay, from the look of things, we'll balance this equation. So now what do we have here? We have what? Prop what? Prop 1 in or prop in. It's the same thing. We can call it prop 1 in or prop in. Alright. So this is how we can use the hydrogenation of vicinal dihalide to get what? Our corresponding alkene. It's as easy as this. Alright. Now let's look into another preparation of alkenes. Alright guys, now finally the last preparation of alkenes we are going to be looking at. This one I think is the most complex inside all that I've given to you guys, but we are going to see the way we can actually break it down in a way we will understand. Okay, so the last one, which is the third in this video, is what? Reduction of Alkynes. I know we haven't treated alkynes, but from everything we've been learning from our past video, I believe we know what an alkane is. We know what an alkyne is. An alkene, sorry, and finally alkyne. Normally we say alkenes are single bond, alkenes are what double bond, and alkynes are what triple bond, obviously. So now, from that information, we can deduce that alkynes can be what? Now, remember, don't forget, reduction of alkynes. We are what? Using, remember, it's the preparation of alkenes. And we are going to reduce alkynes to get alkenes. So first of all, we have to know what to do. First of all, we have to put our triple bond. It must be an alkyne. Carbon to carbon triple bond. Now, this is how we are going to write it in general formula. Okay? But now, look at this. An alkyne can appear like this. This is how we normally represent it. But most times, sometimes, these alkynes can actually possess what? Substituents. So, we can decide to leave it like this. We can decide to leave it like this. Okay? So now, but for this preparation, it is going to carry what? An alkyl radical. Now, this is how it's going to be, because it's a two-way reaction. So let's draw another one, a similar one. It's the same thing actually. Okay, we've written out our alkyne. These are our alkynes, the triple bond, our alkynes. Okay, since we've gotten alkyne, now what do we want to do now? You have to pay close attention. I believe we all know what cis and trans means. Now, in this reduction of alkynes, there is the catalyst we will use. We are going to get trans. There is a catalyst we use. We are going to get cis. Okay. So now, in this one, if we use what? If we use hydrogen molecule, I didn't say hydrogen atom. Hydrogen molecule and what? Lead, Pb. We are going to get what? We are going to get 6. You understand? In geometric isomerism, we all know what cis and trans means. Okay? So now we are going to get 6. The compound now here will be in form of what? 6. Alright? So now, it's not only this guy we can use. We can also use what? We can also use nickel and boron. Note it. Nickel and what? Boron. Alright? And either we use this guy or we use this guy to get what? A 6 compound. An organic compound represented in what? 6. And we know this geometric isomerism about cis and trans they are actually peculiar to what? Alkenes, double bond. Have you ever seen a cis and trans that is single bond or triple bond? No. It's mostly double. It's actually unique to them. Cis and trans. Okay? So now this guy here now, which catalyst are we going to use for this reaction to give us what? To give us a trans. Now, first of all, we're going to use a sodium ion. Or what? What else can we use apart from this sodium ion? It's very, very, very simple. We are going to use what? We are going to use something like this. Yes, now. We are going to use lithium and ammonia. Yes. This is what we're going to use. Either we use sodium or lithium and ammonia. Sorry. Now, everything we use here is going to give us what? A trans. Anything we use here is going to give us what? A 6. Now, remember, we know what oxidation means. We know what reduction means. When we reduce this guy, we are going to reduce him to what? Corresponding what? Alkene. If we reduce an alkene, it will give us corresponding what? Alkene. So you get the logic. If you reduce triple bond, it will give you double bond. If you reduce double bond, it will give you a single bond. It's just like, do you remember in the preparation of what they call it? Preparation of alkenes. What do? We hydrogenate what? We hydrogenate alkynes to give us alkenes. If we now want to get an alkene, The preparation now will now be what? We hydrogenate alkenes to get alkenes. During the hydrogenation, what will happen? The double bond or the triple bond will break down to the corresponding what? Double bond and single bond. You get the idea. Now, the same thing happens here. So now what will happen? We will automatically get the double bond. After that, what will happen? Remember, these catalysts are peculiar for what 6. So we are going to get something like this. This is where the substituent will be, the alkyl substituent, and here is where our hydrogen will be. Now this one is what? 6. Okay, this is what we are going to get. Now in this one here, we are going to have what? Trans. We are going to get something like this. Alright, so take note of them. It's kind of complex, but just remember it. Hydrogen molecule with lead, nickel with boron will give you 6. Sodium or lithium and ammonia will give you what? Trans. It's as easy as that. So with no further delay, let's look into the further advanced reactions that actually alkenes can undergo. Okay now, alright guys, now we've got to the general formula already. So what do? We take an example. So on taking an example, we have to choose a compound that we're going to use. Now, we know first of all it has to be a triple bond, which is an alkyne. So our substituents, we can use what? We can use methyl and what? We're going to use propyl here. Propyl. So using propyl is C3H7. Okay? So now this compound now, remember, we have to use our catalyst. And what catalyst can we use? We can use what? A hydrogen molecule and what? And lead. Or we can use the other one. Like either we use this two or we use the other two. Okay. So now, from the look of things, what is going to happen? We know that using hydrogen molecule and lead, what will it give to us? A 6 automatically. So we can just put our double bond. And what? Since it's 6. Now, how do we know which one is going to be here and which one is going to be here? It's very, very simple. The first one here, which is methyl, is going to come first, CH3. The last one here is going to come here, C3H7. Okay, it's as simple as that. Then we just balance our hydrogen. Now we've gotten our compound. But wait, hope we all know how to name cis and trans alkenes. Okay, it's very, very simple. Now first of all, sometimes this thing can be confusing. You see 3 carbon here, you might start counting it like 1, 2, 3, 4. No, it's 3 carbon. You have to observe it. So, but first we have to observe the longest carbon chain. Obviously, the longest carbon chain is 1, 2, 3, 4, 5, 6. Now 6. So we are going to count like this. Why do we count from here and why didn't we count like this? If we count 1, 2, 3, 4, it will take longer time before we reach to the double bond. And remember, when we're talking about alkenes in our family, we said double bond is priority. Okay, so the double bond is the priority. So we have to count from the one called 1, 2. Okay, we already know this 1, 2. Alright? How many carbons are here? Obviously, there was 6, which is what? Hex. And we know this compound is in which form? Is in 6, right? So we have to name it what? 6 hex what? 2 in. You get it? 6 is the form. Hex, which is also 6 carbon in number, is why it's named hex, the parent name. Then 2 is the position of the carbon holding the double bond. In is the what? Family name. It's as easy as that. Naming the cis and trans is as easy as that. So now, which other compound are we going to use to check the other one, which is what? Trans. Okay? Now, which example can we use to check the other one? Like, we can use something like this. C3H7 as our substituent, which is propyl. Putting our carbon to carbon triple bond, and what? Finally, we use C2H7. Okay? Sorry. C2H5, which is what? This is what? Etap. This is what? Propyl. Okay. Now, which um catalyst can we use to get a trans? Obviously, we can use what? Lithium and ammonia. We can also use sodium as one. Okay, personally, sodium can do it. So now, the sodium ion as the catalyst react with this guy. It's going to give us, it's going to break down the single bond. It's going to reduce it to what? A double bond. Carbon to carbon double bond. Okay, carbon to carbon double bond. And remember, it's a trans, so we have to put the substituents like this. So how do we know which one to put first? Because it's not like this guy. Fun fact, it's the same thing. So we just have to go first. From this side, the first one will be here, C3H7. The last one will be in the other side, the last side of it. So C2H5. It's as simple as that. Okay, guys. Now, what next? Let's balance our hydrogen. After all these are done, what should we do? We look for the longest carbon chain. And obviously, if we count from this side to this side to be longer, 1, 2, 3, 4. That's not what we want. 1, 2, 3. Obviously, that's what we want. So we know the position of the carbon bearing the double bond is 1, 2, 3. Okay, 3. That's the position. Note that. Now, what next do we do? How many carbons are here? 1, 2, 3, 4, 5, 6, 7. Hept. Okay, so now we've gotten the parent name. What do we know about the structure here? Is what? Trans. So it's very simple. We just name it trans what? Het in. It's as easy as that. Naming what? Cis and trans is very, very, very easy. It's just about following the step-by-step processes, and that's all. Okay, guys. Now, what do we do next? We have to look into the reactions of alkenes. Alright, guys, ASAP, let's look into the reactions, further reactions on what? Alkenes. Okay, it's going to be very, very quick and easy. This one is the easiest among the other 2 or 3 and extra I'm going to be dropping here. Okay, so first of all, let's go with this guy. So the first one, what is it called? It's called halohydroformation. Okay, halo what? Hydroformation. Okay, from the name we can get it has to do with what? Halogens. It has to do with water. Okay, so from that now, it's a reaction of an alkene. So what it has to do with what? It has to do with an alkene. Right, like these points are very, pick out the points, they are very essential. It has to do with what? Alkenes. So what will happen? We have our general formula of alkenes to be like this. Good and fine. So after getting this guy, this is our sample, our alkene, our general formula. So now, what are we going to react with it? It has to do with halogens. So obviously, X2, diatomic, we know they are diatomic. Hydro, it has to do with water. Add water. Are we getting it? It's as simple as that. So now, from the look of things, if we are going to get, if we react these guys, what is the corresponding compounds that we are going to get here? We are obviously going to get haloalkanols and hydrogen halides. Okay. All right, so now this is how it's going to be. We're going to get something like this. We're going to get, and you get it like haloalkanols. It will contain an halogen, it will contain an alcohol, and what? Hydrogen what? Halide. This is as simple as that. So this first reaction of alkenes in this video, halohydroformation, it means the addition of alkenes to an halogen in the presence of water, or adding with water to give what? An haloalkanol and what? Hydrogen halide. Is as easy as this. So take note, write it in your book. Hydroformation is the what? Addition of an alkene to an halogen and water to give what? To yield what? To yield us an halo what? Alkanol and hydrogen halide. So okay, now from the general formula, what do? We take an example to see how we can actually see if this equation or general formula is correct. Okay, what do? We can use any example. So let's use propene. Okay, let's use propene. One, two, three. We balance our hydrogen ASAP. Okay, your one. Okay, so now if we react propane with what? Which halogen are we going to use? We can obviously use what? We can obviously use chlorine here plus H2O water to give us what? It's obviously going to give us a propanol containing what? Chlorine. So now from that we can get what? One, two, three. Okay? And now this is the crucial part. Every time an alkene is in a reaction, we have to take note of where the double bond is. Now, the position of the double bond, obviously, that's where what? The chlorine will be. And that also is where the OH group is going to be. So we can just balance our hydrogen afterwards. Okay, from the look of things, we've gotten our compound correctly. So what is going to happen? We are obviously going to have what? A hydrogen halide, which is what? HCl. Okay, so we've actually gotten what we want. Now we can call this what? Propene or what? Prop what? 1N. We can call this guy propene or what? Prop 1N. Alright, so our what? Our product is going to be called what? We are going to call him what? First of all, we are going to write what? This substituent is the most important here. Okay? We know that this guy is in what? The second carbon. So it's going to be what? 2 chloro 2-chloropropanol and what? Our HCl there. Okay, this is how we can actually, this is how the reaction, which is halo hydro formation, looks like. It's as easy as this. You just have to get the breakdown point and ASAP, you know it. Alright guys, now this second reaction, it's kind of going to be funny, but actually is if you get the whole point. Now we know it's a reaction of alkenes, so alkenes will definitely be present in this reaction. So now, first of all, what are we looking at here? We are looking at what? Hydroxylation. That's what we are actually looking at here. Hydroxylation can actually be called glycol formation. Okay? Glycol formation. Okay. The process is called hydroxylation. It's actually going to give us glycol. Okay, but in that we are going to do what? We are going to be looking at the general formula first. Okay, we know it's going to contain what? Alkenes. Let's write it. Now, alkenes. So what is alkenes going to be reacting with? It's going to be reacting with what? Permanganate. And when we mean permanganate, what do we mean by permanganate? We mean KMNO4. When KMNO4 reacts with an alkene, it's actually going to give us a what? First of all, reacting this guy with this, it can't give us glycol except what is in the presence of what? A performic acid. And what do we mean by performic acid? Okay, performic acid is, this is performic acid. The formula for performic acid, this is how we write it. Okay, so When alkenes react with what? Permanganate in the presence of what? A what? Performic acid. It's going to give us a corresponding what? It's going to give us a corresponding diol. If you are wondering what is diol, diol is very simple. It means there is a presence of two OH functional group present. Like the way we have dichloro, dihalides is the same thing diol. We just have two OH present. Okay, so that is that. So which example do we now use? Okay, let's use butene. So one, two. So using butene, this guy, balance your hydrogen, please. Space might not let me do some, but like we have to still find a way across it. Okay. Now this is how what both 2N looks like. Alright. So this being both 2N, let's write it. Both 2N. Both 2N reacting with what? Our permanganate KMNO4 in the presence of what? Performic acid. Okay? In the presence of performic acid, what is it going to give us? It's going to obviously give us a diol. So now, how is this guy going to be? It's very, very simple. Remember, the position of the double bond is priority. So now, first of all, we write our what? Okay? We bring out our 4 carbons. Obviously, the double bond will vanish. To obviously vanish, we will bring down to single bond. So, which now the second and the third carbon is actually in possession of what? A double bond. So this is where our diol will be placed. Now what else to do? We just have to balance our reaction. Make sure they are tetrahedrally linked to each other. Okay. Now from the look of things, we have actually successfully balanced our hydrogen. What else should we do? It's very simple. How do we name this guy? We know that it's 4 carbon. We know there are 2 OH group. So the position of the OH group 1, 2, 3, 1, 2, 3. So it has to be 2, 3 or 2, 3. It's the same thing. So how do we now name it? We name it what? 2, 3 butan diol. Or what? Butan 2, 3 diol. Any of them can go. Okay. So now we are done with what? Hydroxylation, also known as what? Glycol formation. Alright, this one is kind of simple though. It's more like the other one, but it's kind of slight difference. Okay. So now another reaction of alkenes is what? Oxidation with Bayer's reagents. Oxidation with Bayer's reagent. Now, what do we know as Bayer's reagent? Is what? KMNO4. As I said that it's like the other one, but the other one there is a presence of what? Performic acid. But here, what? It's all about what? Bayer's reagent, known as KMNO4. Okay, this one is going to actually give us what? What are we trying to form here? Glycerol is the preparation of glycerol. Okay, so now on that note, what is going to happen? Let's use what? An alkene. And which alkene are we going to use? We are going to use ethene. So using ethene, we already know the formula C2H4. Okay, when C2H4 reacts with what? KMNO4. But now the oxygen in KMNO4 is the oxidizing agent there. So it's the guy that is going to oxidize this guy. Alright, so it's the oxygen here is the most important about the whole reaction. Okay, but the oxygen is gotten from what? The KMNO4. Alright, KMNO4 being a strong oxidizing agent is going to oxidize ethene to what? It also give that's why I said it's more like the other one. It's also going to give us a diol. Alright? But this time around it's not in glycol, it's called glycerol. Alright, so now we're going to have something like this. The double bond will be broken. And what? The position of the double bond, that's where our OH will be. Okay? Then we now balance our hydrogen. Okay guys, so now from the look of things, what are we going to call this compound here? So we have this compound to be what called ethane. Now remember, the double bond is no longer here. So now it's an ethane now, but it's not going to be called ethane because there are two OH group present. So we only can call this guy ethane 1,2 diol or 1,2 ethane diol. This guy is also called glycerol. Okay, so now I think we are done with this guy. We have to look to our final reaction for today, the most complex. There are points I want you to note about this guy called what? Bayer's reagent. Note it in your book. This guy, Bayer's reagent, its primary use is what? It is used to test the degree of saturation in unsaturated hydrocarbon. Alright, obviously from our former class we should have noted that what? We should have noted that alkanes are saturated already. So what do we automatically mean by this? We mean that there's nothing in relation between Bayer's reagent and alkanes. We mean alkenes and alkynes are in relationship with Bayer's reagent. Bayer's reagent is now used to test for the degree of saturation of unsaturated hydrocarbon, which means this guy is used to test for how saturated alkene and alkyne are compared to alkanes. You get it? Now, it all depends on the pH of the medium. That is, because using these guys, it all depends on the pH of the medium. Now, what do we mean? If the pH is acidic, the color is going to be colorless. We know KMNO4 to be purple in color. So if this guy now actually is in an acidic medium, it will what? Change from purple to colorless. But if it's in a alkaline medium, what will happen to it? It's actually going to change from purple to green. Those are points which I want you to note about Bayer's reagent. Okay, so quick, let's look into the final reaction. Okay, alright guys, now finally we are going to be looking at the final reaction, though this one is kind of complex, hard and difficult, but paying close attention and the one I'm actually going to break it down for us, I believe we are going to understand. Now we are going to be looking at what? The final one, which is what called cleavage reaction. Now it's cleavage reaction, and under this cleavage reaction we are actually going to be looking at ozonolysis. Now don't get confused. What do we mean by ozonolysis? It's very, very, very simple. Now I've always told you guys, looking at things like this, first of all you look at the similar things. First of all, we know we are talking about reaction of alkenes, which means we know it has to do with alkenes. And from this word ozonolysis, we already know it has to do with ozone. Okay? So now, I'm going to give you a definition. Please write it down. Now, ozonolysis, this is the reaction between what and what? Obviously, we know it between what? An alkene. Between alkenes and what? Ozone. Between an alkene and ozone to what? To yield what? It's going to yield what? Ozonide. So this is reaction between alkenes and what? Ozone to what? Yield ozonide. Now it doesn't just stop there. Ozonide further reacts to it does not just react alone. It reacts with what and what? It reacts with further react with what? Zinc dust. This guy further reacts with zinc dust and H2O, which is what? Water. It further reacts with what? Water to yield what? An aldehyde and what? Ketone. Okay guys, this is all we need to know about ozonolysis. It's the reaction between what and what? Alkenes, which we are talking about, and what? Ozone. To yield what? An ozonide. I think this is the only odd one here, the odd word. We all know what ozone means now. Ozone is what? O3. We know oxygen molecule to be what? O2, right? O2 is oxygen molecule. O3 now is ozone. Okay, that and that is what we should note. Now, this ozonide, it leaves the reaction and further reacts with what? Zinc dust. Now, this is another significant point to note here. Zinc dust. What is zinc dust? Obviously, it's normal zinc, but it's like in a powderish form, which means it was grinded or something in the presence of what? Water. Okay, to give what? Aldehydes and ketones. These guys are also in the homologous series, which we are going to be treating in our other classes, okay, but not in this video. So now, what next? I will have to draw the general formula on how this reaction is all about so that we can actually understand it. So let's just dive into the general formula and look for an example to back it up. Now let's look into the what? General formula, how the whole reaction actually looks like. Obviously, it has to, from the what definition, we know it has to do with what? An alkene. This means that it can actually what? Be more than two carbon chain. The chain can extend or whatever. So okay, I've said that more than how many times, I don't know. So when an alkene what? Reacts with what? Ozone, O3, okay? When an alkene reacts to ozone, what is going to give us is what? An ozonide. Giving us an ozonide, how does an ozonide looks like? Okay, an ozonide is very easy. First of all, we draw it, you give that kind of triangle vibe or something like that. Okay, and we're going to get something like this. Now, the position of our carbon is going to be like this. Okay, this the vibe is going to give us. Now, these places are actually going to be for the substituent, but this is the O vibes. You get that kind of, this how the structure of an ozonide looks like. So this is the major thing you have to cram a little bit. Okay, so on looking at this thing, what then do we do? We say this ozonide will what? Further react with what? It's going to pass through what? Zinc dust and what? H2O, which is water, obviously. What is it now going to give us? An aldehyde and what? A ketone. So now, aldehyde looks like this. Our ketone is like this. Okay, so now this is how it's going to look like. This is our what? Aldehyde, and this is our what? Ketone. This is our what? Ozonide. This is our what? Ozone. And finally our alkene. Okay, so our alkene reacts with ozone to yield ozonide. In the presence of water and zinc dust, it's actually going to yield us our aldehyde and ketone. Okay, this and this is what I want you to note about this. But now, we can't just stop here. We have to take an example. So, which example do we now take? Now, the example we are going to use, we use something like this. Okay, we use something like this. Now, this compound here, if this compound what reacts with what our ozone. Now, looking at this compound, if you react, we know it's an alkene obviously. If you react with what our ozone. Now, how is this thing actually its ozone form? Our ozone is going to look like it reacts with our ozone and need an ozone. How then is this ozone going to look like? First of all, we'll give that our triangle vibes. Okay, first we'll get our ozone structure correct. Okay, now, okay, then I'll now like put our carbon obviously. Then now, this is where the problem comes in. We've gotten our ozone structure. Now, this is where the problem comes in. How then are we going to fix this thing into this? It's actually going to be easy. Okay? So now, how then do we now fix it? It's very, very, very simple fixing this guy. Now, you see, we maintain this double bond. I told you anytime we're dealing with alkenes, it has to what? Deal with double bond. Alright? So on that note, you see this guy. This guy is what? An alkyl. We're just going to highlight this guy out of here. Follow me. We're going to pick this guy out of here like this. Put him here. C2H5. The way we normally fix alkyls, like when we're doing what? Our cis and trans. You just put it. The first guy comes to this first side. Now, what then is going to be here? Remember, in this whole region, we have actually picked out this guy. What is remaining? CH. We already have our carbon here. Are you getting the whole point now? You just have to balance your hydrogen like this. Are we good? So now, on that note, we look at this side. Now these things demarcate this side. Then the other side, sorry, the other side of the double bond is what we're going to put here. And obviously, there's already a carbon here and there's carbon. Only two hydrogen left. We can decide to put the hydrogen like this. You can also decide to clean out the bond and just put it H2 if you want to write small, but let's leave it like this. This is how actually the ozonide of this reaction is going to look like. You get it? Don't get confused. What we just do after getting the ozonide structure, we have to impute balance it up. So we just pick out the alkyl group, put it first. Next thing, we balance the hydrogen. What next? The other side, we just balance the hydrogen, and that's all. It's as simple as that. But we are not done yet. We have to react in the presence of what? Zinc dust and water. What is going to happen? If you pay attention, you get it. It's the same logic. How we pick this guy from here and put him here is actually how what we are going to do. So we're just from here, we are going to treat the aldehyde first. We are just going to pick it like this. Pick it one. C2H5. What next? The carbon here. We balance our hydrogen. This is our what? Our aldehyde. Okay? We've gotten our aldehyde. Then what next? Our ketone. I think there's no space here, so I'm going to bring it down. It's going to be like this. Our ketone is going to go like this. Okay, from the look of things, we have actually gotten our aldehyde and our ketone. So this is how it actually is if you don't understand, if you are still processing it, you can actually play it again. It can, because it's kind of all bulky and all that, so you can play it again so that you understand. But before that, let's write it out. This is what this is our what? Ozonide. This is our what? Aldehyde. And here is our what? Ketone. So that you don't get confused. So our alkene here reacts with what? Our ozone to give us our ozonide. All that, and in the presence of our zinc and what? Water, to give us a corresponding what? Aldehyde and what? Ketone. So doing this is very, very easy. You have to follow it step by step. Pay good attention, and That's all. Thank you for watching. Make sure you take your sweet drop, okay? Alright.
Hello. Do you have that computer that can flip like this? 360.
Let's have it. Let's have it. Let's have it. Let's have it. Come on.
I'm sorry, my husband. I'm sorry, my husband.
But that big cry, you go cry.
Alright, welcome my true Kemelites. Today we are going to be looking deeper into Alkenes, more advanced.
But that big cry, you go cry.